Hello. In the previous video, I explained the basic setup for a binary random variable. So also we call the distribution of a binary random variable as the binary distribution. So the assumptions are simple. The assumptions required for a binary distribution are that x, a random variable x, is binary random variable. That means takes only two possible outcomes. And probability of success is encoded as p. And then if so actually the second assumption is not an assumption because it loses no generality. Anytime, whenever x is binary, you can write it as p, right? So it is not a problem. It's not an assumption at all. Does not restrict anything. Anyhow, so if these two are satisfied, then we call that the random variable x follows a binary distribution or Bernoulli distribution. Bernoulli is a is an is a statistician, maybe Italian statistician, like maybe 100 years ago, several hundred years ago. Binary distribution with parameter p. It follows a binary distribution with parameter p, or follows a Bernoulli distribution with parameter p. And we simplify the writing as x wiggle binary parenthesis p. Right? So this wiggle usually in statistics it implies a random variable follows this distribution. So and usually parameters are written inside the parentheses. So like name of the distribution and the parameter. So it looks like a like Excel function, right? Or you may have seen like Bernoulli P. Sometimes it's abbreviated to BERN dot parenthesis P, but it differs slightly, but usually it's called binary or Bernoulli. And the point here is there is one parameter, and if that parameter is known, then you know everything. So it's a it's not a summary. It's a summary, but it's a perfect summary. It loses no information writing this way, right? So this is the simplest possible distribution model in statistics, and we can think about other different more complicated models if we need. And of course there are many statistical models, and that they can be understood in this way. Suppose that if some experiment satisfies some assumptions, then a few parameters can fully characterize its distribution. So a few parameters summarize its distribution without losing any information. Contains all the information within a few parameters. And of course, the experiment is it can be like imaginary, but in theory we can think of any experiment. And then as a result, you can think about parametric distribution family. We call this distribution family because if you change the parameter, the shape of the distribution changes. Shape of the distribution may change, but in the end, all the different distributions belong to the same family. They are different only up to their parameters. They satisfy the same assumptions, but with different parameters. Then those distributions are called as a distribution family, a parametric distribution family, right? So examples, which I do not teach in this course. Some examples include the Poisson distribution, the exponential distribution, the gamma distribution. So if you are curious, you may type these names on Wikipedia or on Google. Then you can see some images, the shape of the distributions, and you can see how they differ across different parameters. So if you are curious, you may search for them. And these these distributions are also very important, but I don't teach them because it requires more time to explain how they are obtained and why we are using them. So I'll skip them in this course. Okay, let's think about another example, also a very simple example, coin toss. This is another example of binary distribution, and I'm going to write x equals to 1 for heads and x equals to 0 for tails. And I'm going to call heads as success, tails as failure. But as I said, it doesn't mean tails are bad, just names. And suppose that you throw a coin 5 times and you recorded the observations like this, right? Head, tail, tail, right? HT, HTT, but I used numbers to record the outcomes, so 1, 0, 1, 0, 0. And from this, think about this. Based on this sample 5 trials, what is the probability, sample probability of heads based on these observations? Very simple question. It takes 3 seconds to calculate. The answer is out of 5 times, you see heads 2 times. So 2 times out of 5 times, so 2 out of 5, which is 0.4, 40%. So the probability from this trial, this record, is 40%. Now then, let me ask you a similar question. What is the mean of those observations? So there are 5 outcomes. Can you calculate the mean, the average of those 5 observations? It may take a little more. Try this. If you need more time, pause. And I think it should be easy to everyone. And let me go quickly. The mean, to calculate the mean, you have to add 5 numbers and divide by 5. And then, as a result, you will get 2 divided by 5, so it's also 0.4, right? What I want to show, calculating the mean is too easy, but what I wanted to show you here is that the probability of success equals the mean. So 0.4 here, the answer is 0.4, and also answer is 0.4. They are the same. It is not a coincidence. They are always the same. This is one of the most important properties of a binary distribution. So here I'll explain the property in this way. So any binary distribution has 2 possible numbers, 0 and 1, and when you calculate the probability of success, you have to count the number of successes. Number of successes will be counted for the probability of success, and then actually it's counting number of ones because 1 is success. And when you calculate the mean, on the other hand, when you calculate the mean, what you have to do is you have to sum the numbers, right? Sum all the numbers. But when you add 1, 0, 1, 0, 0, adding 0 does not change anything. 0 does not change the result at all. So the summation depends only on ones, right? So in this summation, you may erase zeros. It does not matter if there are more zeros. Even if you see more zeros, that does not change the summation. The only thing that matters here is how many one you have, how many ones you are adding, right? Here, because there are 2 ones, the sum is 2 because you add 1 plus 1. If there are more ones, then that would increase the sum. So what I want you to observe here is that summation is going back to, it's actually there is no difference between summing ones and counting ones. If there are 10 ones, then their sum is also 10, right? Counting and summing of adding ones are the same thing. They are doing the same thing. So in calculating the probability and in calculating the mean, the numerators are the same. Therefore, think about this. Probability of success is the ratio between the number of successes, number of ones, divided by the total sample size. And on the other hand, the mean of x, expected value of x, equals the sum of numbers divided by the sample size, which is the same denominator as the probability. And we just learned the numerators are also the same. So in the end, this probability equals the expected value. So this is true for any binary distribution, regardless of the value of the parameter. It doesn't matter if p is 0 or if p is 1. Does not matter or like what value the parameter takes. So as a result, I would recommend this kind of interpretation. I want you to understand what is the mean. So then now let's think about going back to the mean. Actually, in a binary distribution, the mean doesn't mean anything because to calculate the mean, we have to make the random variable a numerical variable. So the variable had to be a number. That's why we wrote head as 1 and tail as 0. But as I said, it doesn't matter if you change 0 and 1. So 0 for head, 1 for tail. There is no difference. Or you may change like 1 and 2. Still, there is no problem. We are using 1 and 0 because that is the standard, that is the convention, and that is the most convenient way. However, 0 and 1 do not have any meanings as numbers. They don't mean anything as as a number. It doesn't mean 1 is greater than 0, or you cannot multiply them. So, and then even more confusing is, what is the average? The average was 0.4, but there is no outcome such as 0.4. 0.4 means nothing as a number, as an outcome, right? So it's very difficult to interpret what the mean is in a binary distribution. So a better interpretation I recommend you is this. If you calculate the mean, okay, the mean is 0.4, but we also know that the mean equals the probability of success. In this case, success is head, so we are calculating the 0.4 was the probability of success, which is a better interpretation, right? Otherwise, 0.4 does not have any meaning as an average. So, and also and it is only about interpretation. Even if the mean doesn't the average doesn't mean anything, still it satisfies all the nice properties as a mean. For example, we learned the mean preserves the linear relationship when you transform a random variable. It holds in this case, even in binary distribution case. So the properties as a mean will be preserved, but you just need to change its interpretation. Change the interpretation to the probability of success. That is what you need to keep in mind. Okay. It took a long time. I will use another example in the next video to explain this idea. And from there, we will extend and generalize the model. Okay, see you in the next video.